Okay, so last time, hopefully you guys followed along and were able to watch the video where I re-derived centripetal and um, tangential acceleration using vector notation. Um, in this video, I want to kind of just really tie that line off. And so this video is, to be honest, it's outside the purview of this course proper. So if this is your last physics course that you'll ever have to take, you really don't need this video. And the stuff in this course, in this video, will not be tested on at all. But for those of you going on to study engineering or physics, I want to rewrite some of the things that we have seen, and I'm going to rewrite it using a cross product. So it's very common that rotational quantities have can be expressed in terms of cross products. So I want to show how that comes about at least a little bit. Okay, so last time we showed, well, let's kind of go through our definitions here. We've defined a coordinate theta, a coordinate derivative omega, which is just theta dot, and we've defined another quantity called alpha, which would be the second derivative of theta with respect to time, or the first derivative of omega. Okay, theta and omega and alpha are all scalar quantities. They aren't positive quantities. You can have negative angles. Okay, so it's not like the magnitude of something, but they're scalar quantities. And it's an angle, 2 pi, right? It's just an angle. It's a scalar. Okay. On the other hand, we found that once we had this, that because there was a relationship between x and y and theta and r, the radius, that there were vectors we could define related to the theta and r coordinates. Maybe we should put r and theta here. So there's a unit vector in the direction of increasing radius, and then there's a unit vector in the direction of increasing theta. And we call those r hat and theta hat. So we had r hat is a unit vector, and it points in the direction of increasing radius. So that was equal to cosine of theta x hat plus sine of theta y hat. It points in the direction of increasing radius. In addition to this one, we had theta hat, which points in the direction of increasing theta, increasing angle. So it'd be tangent to a circle. And we worked out a formula for it, and it was minus sine of theta x hat plus cosine of theta y hat. Okay, and you can check those are unit vectors. They are perpendicular. We can check that they're perpendicular because we can take their dot product. So let's do that, actually. Let's work out their dot product. R hat dot theta hat equals, remember, radial direction is supposed to be independent of the angular direction, so their unit vectors should be perpendicular. So the dot product should be 0. And let's see. So I take the dot product. That means I multiply the x components, and then I add that to the sum of the product of y components. So that becomes cosine theta sine theta with a minus sign plus cosine theta sine theta gives 0. So in fact, they're perpendicular because one of our formulas for dot product is the dot product between two vectors A dot B is simply the magnitude of A times the magnitude of B times the cosine of the angle between them. And cosine of 90 is 0. So if you get a dot product which vanishes, then the angle between the vectors is 90 degrees. Okay? While we're on a roll here, let's go ahead and take the cross product of r hat and theta hat. Now, there are two ways you could do this. You could either just picture it, okay? So we have a formula for the cross product. We can do, let's do r hat cross theta hat. So the magnitude of the cross product is going to be the magnitude of r hat, 1, because it's a unit vector, times the magnitude of theta hat, 1, because it's a unit vector, times the sine of the angle between them. But the angle between them is 90 degrees, so it's 1. So the magnitude of this thing has to be 1, and it has to point according to the right-hand rule. So let's draw a circle here, and you'll see where this is going. So if I have a circle in the xy plane, so I'm imagining that I've got the x-axis here, the y-axis there, and the z-axis here. And today, I brought some extra markers. So if I pick a point here, my marker, which doesn't work great. See, some things are the same as in class at JCC. Okay, so pick a point here. R hat at this point would point kind of radially out in the xy plane. Theta hat would point along the circle in the direction of increasing angle. And if you work out r hat cross theta hat, you take your hand, your right hand, remember first step is to sit on your left hand and use your right hand. I'm going to label these things. R hat, and here we have theta hat. You take your hand and align it with r hat and curl your fingers in the direction of theta hat, and the answer points along your thumb. Well, for a circle in the plane, in the xy plane, my thumb now is pointing towards z hat. So we learn, in the z direction, and it has length 1, so it's going to be z hat. It points in the positive z direction. So what we learn is, in fact, r hat cross theta hat equals z hat. Okay, so that's kind of just an interesting curiosity at this point. All right, but we have these vectors, r hat, theta hat, and then if you take a cross product of those two vectors, you get something in the third direction, which would be the z direction. Okay, now, at this point, I want to say theta by itself is a coordinate. It's a scalar, it can be positive or negative, but it's just a number representing an angle. Theta hat is a unit vector in the xy plane, and it points along the circle. Okay. All right. So hang on to those things, those facts. If I had more board room, I would leave that stuff on the board, but I have to move on. Okay. What we found last time is that you could describe a position to an arbitrary point in the xy plane, and let's just focus on things which are moving around in a circle. So we want to assume that r dot is, r is constant. Just write that as capital R. And what we found is that the position vector equals capital R times r hat. And we found, if you followed the last video, applying it to the case where the radius is constant, we found that the velocity equals r times omega, a scalar number, these are both scalars, times theta hat. So if you're moving around, if the radius is constant, then you're moving in a circle. If you're moving in a circle, then the velocity vector is always along the circle. So moving around a circle, the velocity is always tangent to the circle. So it's proportional to theta hat. Okay. We can use this. Well, we're going to understand this. We're going to rewrite this with a new vector quantity. So when we have a, let's imagine, let's kind of draw on an XY axis here. X, Y, Z. And we imagine you're at some point here, theta. Remember, theta is measured away from the x-axis, and it would look counterclockwise if you were kind of taking the bird's eye view, looking down from the top. Okay, so there's theta. As it increases, you go around this circle in the plane. We're going to define a new vector. And I apologize, it seems like a lot, and it is a lot. Here in the last video, I've introduced a whole bunch of new vectors you've probably never heard of. It's not really so important for this semester. It's more, sometimes teaching is kind of like playing dominoes, setting the dominoes up in a chain so that you push the button. So once you get them all set up, then as they start to topple, one thing leads to the next. And so trying to set up some dominoes that will eventually get to help you guys probably a full year from now for those of you studying engineering. Okay, so we're going to define a new vector. It's called theta vector, not theta hat. Theta hat is in the plane. It points along the circle. Theta vector is defined, just the definition of it, as theta times z hat, the z direction. So theta hat points along the circle. In fact, theta vector points in the z direction. Theta hat is in the plane. Theta vector is in the z direction. And that seems like a terrible way to define things. It's very confusing. And you're right, it would be, except I'm defining this, but we very rarely would ever use this thing. What we care about is actually its derivative. And then there's really, it'll be clear. It won't be too bad keeping track of things. Okay. So when people talk about stuff that rotates, they usually try to write things in terms of a vector which lies perpendicular to the plane of rotation. Why would you do that? Well, we saw last time, or maybe not last time, maybe 2 videos ago, that we had rotational kinematic equations, which looked a whole lot like the vector kinematic equations. But those were equations for the coefficients, the scalar coefficients, the prefactors. Those kinematic equations did not involve unit vectors. And you might say, well, okay, whatever. But the thing is, if we want to express things, we want to kind of come up with vectors, full vectors, to describe rotational problems. And the vectors can't live in the plane somehow, because if you wait long enough, you just come back, a point, as this object goes around in a circle, eventually the vector comes back to where it started. But So it's at the same point. But on the other hand, when we talk about displacements and things, you think of it as just growing and growing and growing without end. And so that means that somehow the vector description of rotations can't live in the place where it's periodic. And it turns out that the natural thing is actually to make it leak out into the third direction. I'm kind of waving my hands because there's a whole bunch of words that if we were in person, I could say, and I could kind of read the classroom and kind of try to fill in details. And I think I'll just leave it there. This is really just a definition, but it's a vector associated with the angle. It is not pointing in the direction of increasing angle, though. It points in the direction perpendicular to the plane. And if the angle is a positive angle, this will point kind of along the positive z-axis. And if this is a negative angle, it'll point into the negative z-axis. Okay, just take that as a definition. Now, that's not really the one I care about. The one I want is the first derivative of it. Because z is a constant unit vector, I can define a new vector, which I call omega vector. Not omega, not the scalar omega. It's omega vector, which is the derivative of theta vector with respect to time. And that's nothing other than the scalar omega times z hat. Because when the time derivative hits the unit vector z, nothing happens. And similarly, I can define alpha vector and define that to be alpha scalar times z hat. So all three of these angular vector quantities, these aren't coordinate, these aren't angles, these are angle vectors, I guess. I don't know what to call them. They're vectors. They point along the direction perpendicular to the plane of rotation, which for us is the z direction. But you can imagine rotations in more crazy ways. And this thing will always be associated with the perpendicular direction to the plane of rotation. Excuse me. Okay, so I'm defining these new vectors. This is not the unit vector theta. That points along the circle, tangent to the plane. This points along the z-axis. Now, why would I do this, or why would this be useful? Well, what's useful is to note then, so if we had this thing, we show that r hat cross theta hat equals z hat. It also turns out, if you think about it, that theta hat cross z hat equals r hat, and z hat cross r hat equals theta hat. And this is the one I want to use right now. Okay, so what I'm going to do is I'm going to rewrite, specifically, I'm going to rewrite the velocity and also the acceleration equation using our new vectors that I just defined. And this is going to be a key formula. Okay, so remember, z hat cross r hat equals theta hat. So that means I can write the velocity as r omega z hat cross r hat. Let me get rid of my beautiful picture here. I need more boardroom. And now I'm going to use the fact that these are scalars and they can pass through the cross product for free. And I can write this as omega z hat cross r hat. And I find that when you have a rotation in a plane, the velocity can be written as omega vector cross r vector. So that'll be a very useful formula for those of you who go on to take dynamics. All right, let's do another thing. Let's write the velocity vector, and we can write sorry, we can write the acceleration. It's just going to be r alpha times theta hat minus r omega squared r hat. And I can rewrite that, it turns out, as alpha vector cross r vector minus omega vector magnitude squared times r vector. Okay, so so this is something we will use this, or you will use this when you take dynamics. And so I wanted to be sure to at least present it at least once so you can see it. And the idea is everything we did before is right. You can think of what we did before with omega and alpha is more kind of the intuitive picture of what's happening. And then if I want to visualize it, though, it means that we want to think about the velocity and the acceleration and things like that in terms of quantities. So if you're rotating in the XY plane, then you're going to have an angular velocity vector which points along the z-axis. So angular velocity is just the number, the scalar. Angular velocity vector points along the z-axis. And the bigger it is along the z-axis, the faster the object spins around. Okay. All right. So that's on there mostly for completeness and for those of you going on to study dynamics and engineering or more advanced physics. I suppose if there's someone doing chemistry, when you solve the hydrogen atom, you use facts like this too to kind of rework the Schrodinger equation into better shape. Or a rigid rotor, when you want to study benzene or something like that, quantum mechanics of benzene, you would kind of use some of these facts. But for most of you, this is just, I guess, there for culture. Okay. That being said, we're going to move on next to talk about dynamics of rotational problems, which means things like torque and angular momentum associated with rotations. And those are also going to have cross products involved. So from that perspective, and that you absolutely can't get away with without knowing. You have to, that there's not really a workaround for that one. You really have to think of it in terms of cross products of vectors. And in light of that, I suppose this is much more natural too. Okay. All right, I'll stop there.